we'll be overlapping probably on Friday then, because what I'm going to be talking about is second order then. So I've got my schedule here through next. I have my schedule beyond this, but I got my schedule just up here through the 23rd, which is next Friday. The reason for that is I'm trying to figure out the timing on the project. All right, your next major grading milestone is project 1. So if you go back, it's exam 1, project 1, exam 2, project 2, exam 3. All right, that's sort of the order. All right. So I was just trying to figure out the timing on this, whether I'm going to try to put a homework in before the project or not, to help you with it. I couldn't make up my mind on that. I was just thinking about some past experiences and what might help with the project. Okay. Once the project starts, there's no homework really, though. The project is all about the project. All right. Don't start it at the last minute. We'll talk about that. Many people do, and that's bad. Okay. It's you have 2 weeks for it. There's a reason for that, right? It takes time. Okay. All right. So homework 4 is due Friday. All right. So the first couple of problems were meant to be help with the, even if you didn't put them all the way into MATLAB, they're meant to be helpful for you to prepare. All right. So I wanted to look at something here real quick, because it was one thing it seemed like maybe people were missing. So problem 1 here. So 10 cosine or 12 cosine 10t plus 40 degrees. Okay. I'm going to help you out if you haven't done it yet. If I want to convert that guy into, let's say, the rotating vector form, right? So rotating vector means you got 2 vectors that rotate, right? What's the rotating vector form of this? It should be 6 times what? Yeah. Yeah. Okay. So, and I usually put the 40 degrees out there first. And those of you who are getting comfortable with it know that's always going to happen, right? What's the other guy going to look like? In fact, one thing you may have noticed, the other term is always the what? The conjugate of it, right? So it always works out that this guy is, so a conjugate means what? Opposite angle, opposite sine of the angle. Let me say that. Opposite sine. So in other words, negative 40 degrees. Okay. E to the, and what about its frequency? Also negative. Which one rotates in the clockwise direction and which one's the counterclockwise? Left one is counterclockwise, and this one is the clockwise. All right. So hopefully you're familiar with all that now. All right. Now, when I look at this guy, I also said this is the real part of my dynamic phasor. All right. What's the dynamic phasor that goes with that thing? 12 e to the what? J40 e to the J10t. And this guy we called the static phasor. All right, which is really what you're going to use primarily with Yahoo. And this guy is my dynamic, like that. All right, that's the whole thing. Now, what I ask you to do in here is I ask you to compute the value of the dynamic phasor when theta, which is equal to omega t plus phi, equals 60 degrees. So when theta, which is, for this guy, omega t plus phi is what? 10t plus 40 degrees. So where that is equal to 60 degrees. Now, I think what screwed up a lot of people here is it says the period plotted between negative capital T, so -1 period, and 0. Okay. 60 degrees. So one thing to remember here, so if theta and t, if we talk about, right? So if I looked at the sine function, so let's say I had sine of theta, where sine of theta is sine of, let me just say omega t, like that. Okay. Theta over 1 period, theta starts at 0 and ends where? 2 pi or 360 degrees. So 360 degrees or 2 pi radians. For a period in time, if that guy's a time function, then this guy says that a period starts at 0 and goes until when? Goes to 1 period, goes to t. All right, whatever t is. In this case, t would be 2 pi over 10. Okay. So looking at this real quick here, if I solve this equation for time, what period am I going to be in? I'm going to be in the period that exists between 0 and capital T, right? So if I think about the next period, right? So there's also a period that goes from 360 to T to 2 times 360, right? Oops, this should be theta. And there's another period, so this would be my theta. There's another period, or that period in time, I guess. Where does it start? T. And it goes until when? 2t, right? If I'm talking about the period before 0, it would go from negative t to 0. If I was talking about the period before that, it would go from negative 2t to negative t, right? So I'm just trying to get you to think about the fact that theta equals, so in other words, this guy, so we're thinking about these things. These guys are rotating in circles, right? So as it rotates around, right, it goes from, so from your perspective, right, I have this vector that's going to rotate like this. It's rotating in the positive direction. Starts at 0 degrees, comes back to 0 degrees. Starts at 0 degrees, comes back to there. The thing that you need to realize is obviously time keeps advancing. So as I go to another period, if I said to you, tell me when t is equal to 60 degrees, you'd give me a time, right, by solving this top equation here. And if I said, well, tell me when that happens in the next period, you would add capital T to that. And if I said, tell me in 10 periods later, you would say, add 10t. I'm using the definition of a periodic function, right? Which we say if a function is periodic, x of t is equal to x of t plus capital T, right? It's also true if I go backwards, right? It's also true that this is equal to x of t minus capital T. That's just taking advantage of the fact that it's a periodic function. Okay, that's something that you should be comfortable with, but I wanted to touch on that real quick because I got many questions about it. Okay. All right. Question? You look like you're ready to get this motion here.
This might be the face.
Okay. 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 All right. That's good. That's good. All right. Differential equations. All right. That's what we picked up the other day, right? So basically they arise from any system with energy storage. With Yahoo, it's an RLC party, right? So L's and C's are your main interest, right? They're my energy storage elements. RLC circuit has how many storage elements? 2. The L and the C, not the R, right? The R is a user. The others are storage. So if I have 2 storage devices, how many derivatives do I have? 2. Okay. In my transient response, how many exponentials do I have? 2. I have as many exponentials in my transient response as I have derivatives, always. Okay. Now there's 2 parts of the response always. One is the steady state or the particular response, right? I'll call it steady state, but particular is the one that the math guys use, right? It's the response that's caused by the input to the system. So if you look at my thing below here, I've said I've got an input x of t. Now I've got my input in a funny place, all right? But I have an input. Let's come back to why I have it where it is, and then I have an output. And again, I'm being mathy here. I'm calling this x and y. X is my input, y is my output. Yahoo would probably call that V sub C for the voltage on the capacitor, right? What I'm saying is that this output has 2 parts. Y sub C is the transient part, okay? Y sub P is the particular part. It's the part caused by the source. One part comes from the source. One part comes from what I call this reluctance on the part of the energy storage element to change its value, right? A capacitor is not happy being forced to immediately change its voltage, right? That comes from the first law of thermodynamics. If I try to make a storage element change its energy immediately, it fights back against me. All right. So that reluctance gives rise to this thing we call the transient response, which is always of an exponential form. Always of an exponential form. All right. Now, we have basically, and I should touch on the fact I called my input here x of t. I placed it after the voltage source. Now that voltage source looks like it's my true input, right? I put it after that switch. If I were to look at the voltage at x of t, which I can do by doing a KVL around this loop right here. Yeah, KVL is your friend. Circuits is very easy, right? Because there's only three things to it: KVL, KCL, and Ohm's law. All it is. Sounds hard, right? Looks hard because you learn all kinds of different ways of thinking about those, but there's three things, right? If I do a KVL around this loop, right, which I could do, and I know this is not the kind of loop you like to do a KVL around. I know that. All right, x of t, what would that be? Well, not quite, right? X of t would be 0, and then when that switch closes, it would rise up to whatever value that voltage source is. So if this voltage source was 5, this guy would be 5, right? So this x of t would be what I called the other day 5 times u of t, right? What is u of t? It's a step function, okay? So I can think of it that way, right? Now, that also means if I did the voltage across the switch is 5 volts and then 0 volts, right? Because KVL would tell me that, because I got to have the sum of the voltages 0, right? This isn't a circuits class, so I don't want to spend too much time on it, okay? All right. In general, my equation is going to look like this, okay? Lots of derivatives, nth order. I said I got a non-homogeneous and a homogeneous. What's the difference between, first of all, the one that I wrote up here, right? Y is my output, X is my input. Is this a non-homogeneous or a homogeneous? Non-homogeneous. Okay, homogeneous would be if it's equal to 0. All right, the transient response solves the homogeneous equation. Okay, all right, so we're gonna look real quick at what we did the other day. I said typically our source, almost always, I say typically, almost always our source has one of those 4 forms, right? It's a constant, it's a sine wave, it's a sum of sine waves, or it's an exponential, okay? The cool thing about each of those things, for all of those inputs, the constant is an exponential with its exponent equal to 0, okay? The exponential is an exponential, and the sine wave is essentially the sum of 2 rotating exponentials, okay? For all of these functions, anything that's exponential has this really special property that the steady state output has the exact same form as the input, okay? So what that means is if my input, so these are my inputs, and what I've called y sub p, that's my particular solution. This is my steady state outputs. Right? Basically, what it means for me is if I have a constant, how am I going to do this? Yeah. I'm going to start at the bottom, I guess, right? Does that make sense? No, there's no good way for me to cross these over. All right. If I have a constant input, I'm going to guess a constant output, right? If I have an exponential input, I'm going to guess that I have an exponential output. And if I have this kind of rotating crazy guy, I'm going to guess that I have a rotating crazy guy. All right. And that makes everything easy. Now I'm going to guess that, but when I make a guess like this B, I don't know B. All right. Don't know B, but I will always know omega. Okay. I will always know the omega. So we're gonna do an example because I know variables get everybody confused, but omega is always going to be known. Yeah. Does that mean that's always yeah, that's always the case. Yeah. And you may be asking, well, I could do Laplace transforms or something like that to solve it. We're not going to focus on that here. We're going to be doing this whole process of getting the transient and all that kind of stuff. But basically, my output and my input always have the same form. All right, and that's what lets me do this. All right, and we talked about the step function the other day. I talked about that, but what I do want to do is I want to do real quick again the same example I did at the very end last time. All right, so I said I had a circuit that somehow gave rise to this. All right, this function, and somehow I changed my values there. I noticed this should be 0.01 dy by dt plus y of t equals 4u of t. All right, somehow the KVL would give rise to that whole thing. Okay. All right. What we said last time is that there's a 3-step approach for solving this thing. Okay. Step 1 is to solve the homogeneous equation. This gives me the transient response. All right. That in to be consistent with the book, section 7.3, where they do this, I call that y sub c. Okay. All right, which the C stands for complementary. The second part is to solve the non-homogeneous solution, or the non-homogeneous equation. This is where what I do is I guess that solution, and I solve for whatever undetermined coefficients are there, right? So if it's a constant input, I guess a constant output. The sinusoidal input, I guess the sinusoidal output. Exponential input, exponential output. But there's always going to be some coefficients in those things that are undetermined, and I got to solve for them, right? So there's a little solution process that I got to do to figure out that undetermined value. That's what we're going to do in this step 2. All right, step 3, we're going to put them together. All right, and we got some initial condition. There's always going to be, if I have a first order equation, there's still going to be one unknown term here. If I have a second order equation, there's going to be 2 unknown terms that we're going to have to solve for. Okay. All right, so let's solve this guy. So basically, if to go to the transient solution, right? We did this the other day. Basically, what I got to do is I got to get to from the non-homogeneous equation to the homogeneous equation. Just means set it equal to 0. Okay. And notice what I did was I don't write y here, I write y sub c, because I'm specifically solving for y sub c. Okay. How do I start this process? What do I do? Well, I got to make a guess here too, right? What's the guess that I make in the transient response? Is what? Yep, C e to the st. Okay, C e to the st. All right, now that works out to be, in the context of the way they think of this often in circuits, negative t over tau. All right, so I'm just going to write this off to the side here. So S equals negative 1 over tau. This is a circuit's way of thinking here. All right, although it's true in mechanical systems and other stuff too, right? That is, I think in the homework I may ask you for a tau value. That's how tau and S would relate. Okay. Okay. For any physical system, what's going to be true about that S? Always. Oh, sorry. There should be an either. Thank you. I was just seeing if you were paying attention. Right. And technically, I gotta be careful. This is for t greater than 0. All right. That's not true before t equal to 0. Okay. And what's the other thing I got to be careful about here? What's got to be true about the value of c? It cannot be 0, right? This would be, then I'm guessing that y sub c is 0, right? And I know that's not true. Okay. So c is not equal to 0. Now, I just said something there about s. What's got to be true about s always? The value of s. Well, I don't know. Maybe it could be equal to 0. One thing I know that it's not going to be is positive. All right. If that was positive, if s was positive, what does this exponential look like as a function of time? It grows, right? Y sub c is the voltage on a capacitor, right? That would imply that the voltage on the capacitor is on its way to infinity, right? Yeah, it'll blow up before it gets to infinity, right? Because I mean, there's not many things that God said about the universe, but one of them is that you're never going to have infinite energy, right? So I mean, that's not going to happen, right? The world has a finite amount of energy, right? So that's a truth and the capacitor will just obliterate itself before it gets there. Okay. No physical system will ever have a positive value for S. Okay. That's something important that we're going to learn. All right. That's always the case. So in Yahoo's Klein 2112, if you write out a differential equation that has negative coefficients, you messed up. Okay. Because then you're going to get rise to a positive. So that's one thing to, when he's asking you to solve those differential equations, get negative coefficients, you're wrong. Okay. Because the universe won't let you do that. You made a math mistake somewhere. Okay. So one thing important to remember. All right. So I guessed this and then I blabbered. What do I do with my guess? Plug it in. All right. So I plug it in. I say 0.01 d by dt of c e to the st plus c e to the st equals 0. Right. And I take the derivative of the first term. Right. What's the derivative of c e to the st with respect to t? Yeah, the s comes down, right? So I say 0.01, sorry, 0.01 s times c e to the st plus c e to the st equals 0. Now, the cool thing about that is I got common factors in each term, right? I got c e to the st. So I can say this guy is 0.01 s plus 1 times c e to the st, all equal to 0. So what I said the other day is this guy is a times b times c equals 0. Three things multiplying each other equal to 0, right? And I know that two of them can never be 0, right? Which two I don't know, multipliers here can't be 0? C and e to the st, right? E to the st can never be 0, right? Unless I was at negative infinity, which I'll never reach either. Okay. So in this case, I know that 0.01 s plus 1 equals 0. That means s equals negative 1 over 0.01 or negative 100. Okay, so I got my value. That means at this point, I know that y sub c of t is c e to the negative 100 t. Do I know what c is? No. Do I know enough to know what c is? Not yet. Not yet. All right, I will. Step 2 was to get the non-homogeneous, solve the non-homogeneous equation, to get the particular solution. All right, so I have a constant input. What do I guess for my output in steady state? If I have a constant input to this thing, so 4, what do I guess is my output? Constant, all right? But I don't know the value of that constant. I just guess a constant, right? So I end up saying, all right, well, let's let y sub p of t be a constant, b. And I usually get rid of this u at t thing because I don't like it. And I write it like this, equals 4 for t greater than 0. Okay. That'll work for me, right? So what do I do with this? How do I figure out what b is? Yeah, I sub it in and solve the equation, right? So I substitute in b, so I say 0.01 times d by dt of b plus b equals 4. What do I know about the derivative of b? I don't know what b is, but I know it's a constant. But derivative of a constant is 0. So that term zeroes out, and I know that b equals 4, right? So that tells me that y sub p of t, I guess I should be really careful about this. That means it's really b times u of t, right? That's because this is only true. There is no solution before I apply an input, right? So that's that. So normally I will make sure to tell you, you have to tell me for what times is it true. Okay. All right, so I've done that. What's my third step? I said my third step was to get the total solution with the initial conditions. So the total solution is y of t is equal to yc, this was the transient, plus yp, this was the steady state. Okay. And I say that that is equal to c e to the negative 100t plus 4 times u of t. Or equivalently, I'm going to say it's c e to the negative 100t plus 4 for t greater than 0, right? That's a little easier to solve, okay? So, how do I solve for c, the thing I don't know? I have to have an initial condition, right? And I said that y of 0 was equal to 10. So that's equal to c, and then what do? I plug in t equal to 0 here. So what happens to e to the negative 100 times 0? So yeah, c e to the 0. E to the 0 is 1 plus 4, right? That leads me to the fact that c has to be equal to 6. All right. So my final solution here is that y of t is equal to 6 e to the negative 100t plus 4 u of t, or 6 e to the negative 100t plus 4 for t greater than 0. Okay. All right. It's pretty boring. It's the process, right? Now, how do I ask you to enter that in typically in the MATLAB? This is usually the way that I do this. So in this case, I said that my S value was negative 100. And I said that, for a circuit problem, that's always equal to negative 1 over tau, right? So what I do, I think in that first order, when I tell you to tell me what is tau, right? That is tau, right? It's negative 1 over that S value, okay? What I will do is tell you a time vector, and then I'll tell you enter in y sub c, y sub p, and the sum, okay? Now, notice what I did with my y sub p here. What is this? 4 times 1's size of t. Yeah, for every value of t, I create a 1, and then I multiply the whole vector by 4. So it's going to make me a vector of 4s. So I've plotted all 3 of them there together. Okay. You guys are going to tell me which one is which. Which one is the particular solution? The red, the blue, or the yellow? The red, right? This is y sub p of t. Well, it's from where you're sitting. It's red. Yeah, it's the flat one. What's the transient response? The blue one, right? What does a transient response always have to do? Go to 0. Transient response always goes away. What's the total solution always do? Levels off, well, not necessarily constant, but levels off at the particular solution. Okay. So, and I draw that distinction. In this case, yes, it does level off, right? If I look at it, it starts at 10. That was our initial condition. And then it comes down and levels off. Okay. Levels off at the steady state solution. So by the time I get to steady state, it's always the case that y is approximately yp. Okay. That's going to look funny when I have a sinusoid, right? When I have a sinusoid, I'm going to have this kind of transient that's going to eventually equal to a sine wave. Okay. All right. Questions about that process up till there? All right. All right. So let's take another example. All right. Now what I've done is I've said let's have a similar differential equation that looks like it's connected to a sinusoidal source. Now, what Yahoo is going to do in 2112, yeah, he's doing transient responses with you right now. DC circuits are boring. DC circuits can only give you transient responses, right? So the voltages go like this or whatever. And so you worry a lot about the transient response in DC circuits. Okay. What's a typical DC circuit? Well, any digital circuit, your microprocessor, right? Your memory chips, those are all DC circuits. Okay, so that stuff applies there. When we talk about AC circuits, very often we just say, you know what, we know what the transient response is going to do. It's going to be exponential. It's going to last for a microsecond. And then for the rest of the time, it's going to be just floating around as a sine wave. So we only worry about the steady state response. You're always going to stop doing differential equations eventually, fairly soon. All right, because you don't need them. Right? If I make the assumption that I'm only worried about steady state, I use this exponential thing to get rid of a lot of the math, a lot of the calculus. I still have complex number math, but I get rid of the calculus. Okay. All right. So I got this guy, and I get the same initial condition as before. All right. Now, if I want to approach this guy, sure enough, it's the same process. Okay. In this particular case, what do I know? I know the transient response. This guy is going to be an exponential. This is going to be C e to the st, like that. What's the particular solution going to look like? If I have a sinusoidal input, what did I say is always going to be true about the output? Also going to be sinusoidal, right? This guy, I said, is going to be B cosine omega t plus, I'm going to write it as angle of B. Okay, and there's a reason why I'm going to write it. All right? Omega is going to be the thing I know. Omega will be known to me. And in this particular case, what is omega? 300, all right? So I know that this guy is going to be this. He's going to be 300 t plus the angle of B, okay? All right? There are two things I don't know here. What are they? I don't know B. I don't know the angle of B, but I can solve for those, right? That's what I'm going to solve for in step 2. All right? Step 3, I put them together, and I end up solving for, at this point, is where I end up solving for that C, that guy I didn't know up there. Okay? All right. So, step 1, transient response. Okay? What's that? What do I do to solve for that? Yeah. Set the right side equal to 0. And I change my y to y sub c. 3y sub c of t equals 0. Notice one thing is this guy is going to have a transient response that has nothing to do with the input, right? The transient response has nothing to do with the input. It's defined by the properties of the system, by the R's and the C's and the L's, right? So it's because it represents physically what those R's and L's and C's are doing to oppose the change, all right? What do? I guess that y sub c of t is equal to what? C e to the st with t greater than 0 and c not equal to 0. All right, plug that in, and I'm going to end up with 0.1 s plus 3 equals 0, like that. All right, I'm going to skip right to that because I think you guys know what's going to happen every time. All right, my s is going to equal to -3 over 0.1, just like I wanted it to, right? Which is, I think, -30, right? Yeah. Yeah, -3 over 0.1. Okay. All right. Okay. All right. So we got that, right? So now what we said before, all right, is these are my special inputs. All right. I said my special inputs have exponentials in them. If I have a constant as my input, or an exponential as my input, or a sinusoid as my input, I could guess something of the same form. All right. So if I do this, right, basically gives me, I don't know, I expanded step 2 into 5 sub-steps, I guess, right? So what I'm going to do is I'm going to guess that my solution, and I don't want to call this, I want to call this angle B. I'm going to call this B e to the j angle B e to the j omega t. All right, I'll make sure my slides update to reflect that. All right. I'm going to substitute, so where phi is angle B, right? Phi here is angle B. And this is angle B. Okay. All right. What I'm going to do is I'm going to guess this solution. What I'm going to do, though, is I'm going to convert that into the real part of a dynamic phasor, right? And then I'm going to basically convert the whole equation to the complex domain and then go back. All right. And when I get back, I'm going to end up with the values of B and angle B. All right. So let's go through that process here for this guy. All right. So I've got this whole thing, right? So this equation is 0.1 dyp by dt plus 3 yp of t equals 4 cosine 300t plus 20 degrees for t greater than or equal to 0. Okay. So I'm going to guess that y sub p of t is equal to what? B cosine, I said omega is always known. What's omega in this case? 300. 300t plus, not 5, I'm going to call it angle B. Okay. All right. Now, that's the real part of some dynamic phasor. What's it the real part of? B e to the what? J angle B, right? E to the J 300t. All right. Now, maybe what I'm really going to do is write it that way. Because when I do it that way, I can say this is the real part of some complex number B e to the J 300t. Like that, right? I just put these guys together, right? I said B is got a magnitude and an angle. Okay. All right. So I just made basically what I did is looks like now I only got one unknown, right? Because basically I got a complex number. So I put those two unknowns together into one package. Yeah. Mm-hmm. Yep. That's what it's saying is I can put those together, right? So this is a, you know, if this guy's in front here, right? So that guy is going to be a positive number, right? I'm not going to have a complex number in front of my cosine because this is a thing that exists in the real world, right? So and the angle is an angle. So when I bring them together here, those are one complex number. I got a positive magnitude and an e to the j angle of b. All right, so I've put those together as one complex number. All right, now that was step 1 of my process. Step 2 of my process was basically to convert the non-homogeneous equation into a dynamic phasor equation. Okay, so basically it says, all right, 0.1 dyp by dt plus 3 yp of t is equal to, all right, so help me convert 4 cosine 300t plus 20 degrees. Give me the dynamic phasor that goes with that guy. 4 e to the j 20 degrees, 300t. Okay. And we've said that y sub p of t is equal to b e to the j 300t. Like that. Where b has got a magnitude and an angle. Okay. All right. So what do I do with that? Well, I substitute it in to that equation. Okay. So I say I have 0.1 times d by dt b e to the j 300t plus 3 times b e to the j 300t. That is all equal to 4 e to the j 20 degrees times e to the j 300t. Like that. All right. So now that's substituted in there. What do I do? Take the derivative, right? I take the derivative here. So what I do is I say 0.1 What's the derivative of that guy? J 300, right? 0.1 times J 300 times B e to the J 300t plus 3 times B e to the J 300t is equal to 4 e to the J 20 degrees times e to the J 300t. Now, no derivatives left to do. But what term appears everywhere? Well, yeah, e to the J 300t appears in all those terms. Now, the really cool thing about this, and this is why differential equations become a not thing with Yahoo eventually, is what? All time dependence is gone. There's no time left in that thing. To do the steady state stuff, turns out all I need is the static phasor to do the analysis. And that simplifies all of the analysis eventually. Okay. All right, you'll see that as you go. But basically with this, I have that I still have a B common in each term. So I'm gonna say I got B times J 300 times 0.1 plus 3 equals 4 e to the J 20 degrees. All right, that looks like one equation. It's not. How is that not one equation? What's the trick? It's complex. So there's an equation for the magnitude, and there's an equation for the angle, right? There's also, I could say for the real part and imaginary part if I wanted to, but for the magnitude and for the angle. So I have B times J 300 times 0.1 plus 3 equals 4 e to the J 20 degrees. And I can say if I want to, that this is B e to the J angle B, right? So when I'm looking at this guy's going to be B e to the J angle B, 4 e to the J 20 degrees over J 300 times 0.1 plus 3. So that's two complex numbers on top of each other, right? If I said, okay, well, this is two equations. The equation for the magnitude of B is what? What do I do? So I've got complex number divided by complex number. Divide the magnitudes, right? So it's 4 divided by, what's on the bottom? Square root of, well, yeah, 3 squared plus 300, I guess plus 30 squared, right? I guess you could do that. Plus 30, yes, thank you. So 909, yeah. All right. So is that, all right? And then there's one for the angle of B, right? The angle of B is the angle of the top minus the angle of the bottom. What's the angle of the top? 20 degrees, right? 4 e to the J 20, right? So the angle of the top is 20 degrees. What's the angle of the bottom? Arctan 30 over 3. All right. So I solve all that, and I'm going to get some numbers, right? So for B, I'm going to get 0.1327, 0.1327. And for the angle, I'm going to get negative 64.2, what did I say? 0.2894 degrees, like that. Okay. So that says that this guy, so B is 0.1327 e to the negative J 64.2894 degrees. This guy was a static phasor, we said. Well, what I said was that my output was B cosine, so magnitude of B cosine 300t plus the angle of B, which is the real part of B e to the J 300t. Right? So now I've figured out that what y sub p is equal to, right? Y sub p, and this is actually my last step, is equal to 0.1327 cosine 300t plus the angle of B, which is actually a negative number, right? It's negative 64 degrees. And now I've got it, right? So that's my last step, right? I got it back to the trig function. And so I end up with this whole thing here. That, how do I figure out? I still got an unknown. So this is where I want to figure out that unknown C. How do I figure that guy out? Try a lot, right?
Yeah.
Y of 0, it's pretty easy, right? Y of 0 I said was equal to 10. Right? So what do? I say 10 equals C e to the what? E to the 0. That's 1, right? Plus, now what do I do with this ugly guy? Right? So it's 0.1327 cosine what? Yeah, negative 64.2894 degrees. Those are all just numbers. And I can solve for C. All right. Yeah, they're ugly numbers, but they're numbers, right? Now we'll look at this more on Friday, but if I look at those two guys together, right? Now it's hard to see the yellow one here, but which one is the steady state and which one's the transient? Yeah, all right, sorry, that's my y sub p. This is this. Now the blue here is my transient y sub c, and the yellow, which has them together, is y. Now again, it's hard for you guys maybe to see that yellow, but as you look at this, right, what do you notice happens with the total solution, the yellow one, and the particular solution, the red one? They line up, which is what they should do, because what's the transient response do? It always becomes 0. It's gone, right? Transient response is always gone. Now this is the beauty of it, right? Because look, this guy lasted for 0.2 seconds. If your circuit with Yahoo is on for 2 hours, then basically the transient response is dumb. I don't need to know that much about it. Now it's useful. I shouldn't say it's dumb. It's useful in some cases, but if I only care about the other 2 hours, then I can just solve to get the particular solution.
What time and what you use?
The transient matters for stuff like controls and things like that. Yeah. So we'll look at more like this on Friday.